So let me just quickly recall. So until now, we've been doing discrete random variables. So we've been doing X is as a sample space. And I took the space of all events to be all possible subsets of S, the power set of S, and I had a P which is a probability on S. And I largely took S as countable. So I only took S as countable. It's countable or finite or infinite. So now what I want, and then we discussed X from S to T as a discrete random variable. So X from S to T, we've been discussing discrete random variables. This is where we are at, and then here, of course, for these guys, we know that the probability mass function, the PMF, probability X is in T equal to T for all T in T, kind of provides the entire distribution of X. So the PMF, the probability mass function, and it provides the entire distribution of X. So one of the features of these models so far are the following: that the outcomes of the experiment, outcome space of the experiment, so let's say outcome spaces, are all are countable, countable either infinite or finite, like I said. Like we've noticed that the number of trials to require the first head was natural numbers, was a countable space, or if you roll a die, you've seen the example that it's just finite 1, 2, 3, 4, 5, 6. Thanks. Now I want to deviate from this setup. I want to go to a setup that falls outside this. So here's a question that I'd like to pose today. So I want to go outside the setup. So here's the first question. What if we want to choose a number in the interval 0, 1? So how to choose a number uniformly, whatever that means, uniformly, or maybe instead of uniformly, let me use the word random. How to choose a number randomly from the set, the interval 0, 1. So here by randomly, I typically mean that every number is equally likely to be chosen. So I mean I want to replicate the uniform distribution. Very good. That is the question. Now one thing is immediately clear, that the set S01, let me call the set S is equal to 0, 1. The set S01 differs from what we've been doing so far. S is not countable. S has uncountably many elements. Let me just write that first difference. First difference is that the first difference S equal to 0, 1 is not countable. There are uncountably many elements in 0, 1. There's no second element, no third element, no fourth element. There's not even a first element. Then the other thing is that once you have this understand the difference, then the question becomes: can we assign probabilities to elements of S to answer question 1. So this is something that one can immediately consider as a relevant question. Excuse me. So until now we have only done countable spaces S. Now I have a new setup S equal to 0, 1. Can I do that? So what today's class will do is that I will illustrate two things. This is very much possible. But however, one must be aware that there are technical difficulties to overcome. And the key I will try and illustrate. I need to develop a new setup. I need to develop. I won't say develop. I need to sort of define a precise setup. And just one quick recall before I sort of go on to this these two steps is that I don't know if you sort of pay attention. I'd always said that this was a temporary definition of events a long time back, way in the beginning of the course. Very good. So let me just quickly recap this page a little bit. You can see everything in one shot. Very good. So the idea is that I want to now understand how to work with a setup, because it's a natural question, right? How to work with a setup where I have to choose a number between 0 and 1. The set S is not countable. So in that sense, one has to sort of be a little careful to see what are the new nuances in assigning probabilities to elements of S. And we've been not avoiding it because it's not possible. It's just that it requires a new setup, so which we will discuss. But before that, I will now try to sort of illustrate the technical difficulties one needs to overcome before I just give you the answer of how to set things up. Thanks. Okay. So let me leave this page. Let me go to the next page. So what are the key difficulties? So let's try and answer. Let's try and go step by step toward the key difficulties. So let's see. So the key technical obstacles for question 1 or question 10. So the first is that so let's go back. Let's recall. In the discrete setting, so what did uniform mean? Uniform meant to us that every outcome in the sample space was equally likely. Right? Meant that every outcome in the sample space S was equally likely. So let's say we emulate the same thing here. So this would imply that S equal to 0, 1, and if you do it sort of literally, you do a literal translation of what we meant by the green part. Okay? Every element S is 0, 1, and every outcome is equally likely. Very good. So that means equally is Y is missing. Very good. So that means let's say, so therefore let's say 0 less than P less than 1 or less than or equal to 1, and let's say probability of a single event, let's say X, is equal to P for all X and S. So therefore, this is what we would do literal time. But let me do a simple idea. Let me do a simple illustration why this will fail. So why this fails is the following. So what's the obstacle? So why this fails? This fails is the following. So let's say why. What's following? So what I do is I take the set E to be the set, let's say 1 over n. Okay, so 1 over n bigger than or equal to 2. So that is half, 1/3, 1/4, and so on. Now I clearly know by the axiom of probability. So if there was a probability on S, then probability of E would be equal to the sum over k equal to 1 to infinity or 2 to infinity in that case. Probability of 1 over k. So now let's do an intuitive calculation. Each of these is P, because each of these is P. So there's going to be P plus P plus P and so on and so forth. Right? That's what you think of this intuitively. Now, clearly, if the series on the right hand side converged, then the only option for P is P to be 0. Then P has to be 0. Because if P is positive, then the right hand side will diverge to infinity, and the left hand side is finite number. It's an automatic contradiction. So the only way this can happen is P is 0. So therefore, the first thing we notice is that if you do this, P positive cannot happen. Okay, very good. It's okay, fine. I mean, you can say, okay, what's wrong with this? It's okay. P can be 0. It's not wrong. But then there's a problem again. So now, what is the problem now? So I have S is 0, 1. A probability of X equal to P, and P is 0 for everybody. So you could naively think that, okay, fine. Now, so let me write step 2. So this is part 1. So part 2 of the analysis, you can say, okay, fine. Is there a problem with P being 0? So you could come and say, now S is sample space. S is equal to 0, 1. And we know probability of S, capital S is equal to 1. Because P is a probability on S. That's how we think there's a probability on this. Then is this not valid? Then what you could say is, okay, fine, I'll say probability of S is the same as the probability of union of little s in S of the events, let's say union of X in S. Let's say I'll write X in 0, 1, because S is 0, 1 of the events X. Now you could say, okay, fine, that's the same as that's equal to the sum over X in S, X in 0, 1, probability of X, and that's all P. That's all equal to summation over P, which is all 0 now, because 0, and that's equal to 0. So you might immediately conclude there's a contradiction. But this may not be a strict contradiction, because we have done one violation, and that's the following, that you may already noticed that at this step is not necessarily valid. Right? And why is that? Because of the following fact. So what does P probability means? P probability means that if EKs k equal to 1 to infinity are disjoint, then the probability of the union of k equal to 1 to infinity k is the sum of k equal to 1 to infinity p of ek. Okay. And the key thing was that this collection is countable. This collection is countable. It's only allowed for countable disjoint unions. Right? Countable sequence of events. And here I have an uncountable. Because x is in 0, 1 is uncountable. Right? So union over x and s of the event x is uncountable. So that's why this step need not be valid. So this mistake we made, so there's no contradiction yet. So as of now, somehow we have sort of come to this idea that if we were to assign a probability on S to simulate the fact that we had a equal likely experiment, then the unfortunate part is that the probability of every single outcome is 0. And there's no immediate contradiction to this idea that that this is an invalidate probability of S equal to 1, because if you do the calculation, probability of S is equal to probability of the union of elements in S, and try to use the axiom of probability to write it as a sum, that step is not valid because S is uncountable. So there's no contradiction yet. But somehow we have to come to grips with the fact that if you have an outcome, if you have an experiment with an equal likely outcome experiment on 0, 1, interval 0, 1, the probability of every single outcome has to be 0. There is no other model that will work. That's because I did use the axiom of probability correctly in this step. In this step, I used the axiom of probability correctly because I have a countable sequence of events. So now let's see. So now that means we have to do something different to overcome this this understanding of ours. Still, now we're still stuck with the following idea that I need to understand how to put uniform probability on the. Let's go back. So how does one overcome this? So what's the next second level obstacle now? So what's obstacle 2, let's say? Or it's not obstacle 2, obstacle itself, because we are not come to obstacle 2. Obstacle is that, so now probability of x has to be equal to 0 for all x and s. This we know. Now from this, how do I compute probability that the chosen point is between, let's say, 1/4 and 3/4? How do I compute this? So now I can't simply add up the probabilities of all points between 1/4 and 3/4 because that's an uncountable unit. I will have to do something different. So I cannot just say this is also 0. That's not quite right. Somehow there's something else that I have to understand about what is uniform. So the key is to understand what is uniform. So the first thing observe is cannot sum over probabilities of each outcome in S, in the interval, closed interval 1/4 and 3/4, as the set is uncountable. So I have to come up with some other understanding of the word uniform. Okay, so after we understand what do I mean by uniform, so the key resolution to this problem is the following. So let me write down in, let's say, some other color. The key step in resolution is the following: is the need to reinterpret what we mean by uniform. So we need to interpret correctly what we mean by uniform, that is, to choose a number equally likely in the setup when S is interval 0, 1. So in this situation. Very nice. So this is something we have to understand now. So what do we mean? So we first thought naively that just means that picking every number equally likely, and that gave us an odd answer. Let me recap that for you. Where is it? Here. Very nice. So let me just quickly recap that idea. Let me go slowly. So on the right hand side, I showed you that if I wanted to choose uniform and every number was equally likely, then that P has to be 0. Can't be anything else. And first I thought, okay, I have a contradiction, I can't do this, but this isn't quite a contradiction, because probability of S equal to 1 is not validated by this calculation because I'm doing an uncountable. But then if it's not a contradiction, how do I use this? So if I use this in this fashion, if I want to do this, even if I know this is 0 for every X in S, it doesn't help me compute the probability of 1/4. So the key step is I have to somehow reevaluate what I mean by uniform in 0. Let me just copy this, pull it up. Let's see if I can do it in one shot. Excellent. Well done. Pull it up a little bit. Very good. Well, so let me try and now work towards that. Let me try and work towards how I want to interpret what uniform is. So again, I'm now going to force you to an answer, and you have to believe that's the only answer. Of course, that takes some work. See, it would make sense in the following. Let me try to illustrate how it would make sense. So what's the resolution? Let me see. So one way to resolve this whole thing is the following. So it would be tempting and perhaps correct to do the following. So I have the interval 1/4 and 3/4. That's the interval of interest. Interval or set or event of interest. So what I would do is I would say I would like a probability on S. So we would like a probability on S. Would like to construct a probability on S or define a probability on S such that so now I have the interval 0, 1. So let me have the 0, 1. 0, 1 right here. 0 is right here. 1 is right here. I have 1/4 somewhere here. 1/4 somewhere here. 1/4 somewhere here. And 3/4 somewhere here. And such that the probability of finding a point, my chosen point, is somewhere inside this. So should be proportional to the length of the interval. So what I would do is I would say that the probability of finding a point in 1/4 and 3/4. I mean, I can use the same color as the brown one. So the probability of finding a point in 1/4 and 3/4 should be equal to a half. Why is that? So my loosely worded logic for that is as 1/4 and 3/4 is half the length of 0. Length of 0, 1 is 1, length of quarter, 3/4 is a half, and that's why I think that the probability of this should be half. Let's say this is how we want to think about it. Then comes the next difficulty. Then you could go and say, okay, fine. Now, you could say now, good, if this is what I want, then I can say, let's do the following. Let's do the following. I take an A, a subset of S, which is equal to 0, 1. I define the probability of A is equal to the length of it. So let's say this is one option. This is option 1. Maybe I should just write this in a different color so I can write the red properly. Very nice. You can do this. Very good. Let me get this to this color. Very nice. Okay. So this is one option. Option 1 is this. So now there is no contradiction yet, because if we can do this, then as of now there is no contradiction yet. No contradiction yet to our previous understanding, because the probability of the singleton x, you could think of it as the probability of the interval xx, just this, which is again 0. The length of that interval is 0. So there's no contradiction to earlier calculation. And also further, this is one thing, and further, probability of S is the probability of the open interval 0, 1, which again, the length of the open interval 0, 1 is same as length of closed interval 0, 1, and that's just equal to 1. So you might think that, okay, you're on your way. So very good. So you're on your way. Great. So we're very happy that we have achieved something. The previous calculation is not destroyed. The length of a singleton point is 0. Length of any set A is the probability of any set A is the length of A. That doesn't contradict the first axiom probability, the probability of S equal to 1. And perhaps the countable additive axiom still holds. And also intuitively, our understanding is verified. The probability of 1/4, 3/4 comes out to be a half. So the probability of finding a point in interval is equal to the length of the interval. But now comes the unfortunate fact that this also is not possible. So why is that not possible? Let me illustrate that for you. Let me move this across. Let me see if I can get this across. I'll try one last time. Okay, I'll forget. So maybe I should do this in blue. So I think it's sort of an obvious. It's not so. Maybe I do some blue. Let me change the color to blue. Let's say. So I can sort of. See. Okay, good. Okay, yeah, I want this in blue because I don't want it to be. I want to say why it's not a contradiction. Right. So now there's no contradiction there. And we are on our way. But alas, the unfortunate fact is that this is a little sad. But this one I cannot show it for you here. This you learn in an advanced course, perhaps. It's not in this, not in this, in the scope of this class. See, while it's length of a singleton point is okay, we know how to define length is this. We know length is 0. Intervals we know. Let's say closed, open A, closed B, or anything we want. The length will be just we can think of it as B minus A. Right. And let's say open AB also the same thing. Closed AB also same thing. And then let's say closed A, open B. All these sets have the same length. Let me see if I can get the right. So all these things we can do. It's not a problem. for any a and b in 0, 1, all this is okay. But the difficulty is that while this part is okay, the sad part is that that it is not possible to define length for any set A. That's the sad part. So it is not possible to define length for any subset A of 0. This is something you have to believe. I can't show you why it's not possible right now, but typically it's not. There are sets in A, subsets of A in 0, 1 for which you cannot define length. So let me maybe mark this whole thing in blue so that this is all possible. This is all okay. Color. Very nice. So this is the stumbling block. This is the key obstacle that I can't do this. This is a huge obstacle that I can't follow through with this idea because I can't define length for any set A. So now what do? We don't sort of say, okay, we're done now. Let's forget about it. We can't do the experiment. So what we do is, I will discuss in the next class, is the following. So what should we do? So the resolution is the following. Let me see if I can get that pen again. Very good. So the resolution is the following. So the key stumbling block was we couldn't define A, length of A for any set A to sort of understand the uniform distribution. So what we do is we need to reconsider what we mean by events. So the old definition that an event A implies that A is subset of S is not going to work. I guess here I have to go the reverse way. I just meant that any subset of S is an event A. Is this something we have to rework? We have to reconsider this. We cannot work with this. That's one thing. But we also want something, right? What do we want? We want to choose a number uniform in 0, 1. Right? So we want S in 0, 1, and we want to choose a number uniformly. Right? This is what we want to do. So at the very least, what all events we need? We need events of the form. We need events to include A. We need events to include intervals, right? So by intervals are intervals of singleton point also is an interval. It's okay, intervals. So I mean that any interval. So if you just stretch your mind a little bit, if you look at the axioms of probability, that will sort of imply that you will need to include all possible combinations of unions, countable unions of intervals, their complements, and various combinations of these two. Right? So you will need. So this of all these things you need to do of intervals. So events should include all these two. So one needs to define an event space carefully to include all these possibilities. So this is what one needs to define events to sort of understand both these conclusions. So we will come back and in the next class try and understand this, how to define events so that I have this resolution. And just to recap, let me just go back and recap. What were we after? We were after the following fact that come all the way. So I need this resolution. I also need the following. I'm not giving up on my goal. I start off with this goal of trying to choose a number uniformly in 0, 1. I want to keep that goal. But as I keep that goal, I want to I understood the first key technical obstacles, that every singleton point has to have probability 0. Otherwise, my probability axioms will give me a contradiction immediately. That in itself is not a contradiction, because it doesn't violate the chance that it could happen that probability of S is equal to 1. And that we resolve by saying, okay, fine, I will take it to be, I take the probability to be the length of the set A. And given our old definition that every subset of S is an event, you would like to define the length of any subset of A. But unfortunately, that's not possible. That fact, you must take it from me, that it is not possible to define length for any subset of 0. But then I still don't want to give up. I still want to carry on. So what I said was, maybe the resolution is the following. We don't work with all subsets. We work with only some subsets where we can define lengths. And for that, I said, let's start with intervals. Okay, we can define length of intervals. But then if you want to do some probability on it, you must allow all possible unions of intervals, countable union intervals, their complements, I'm taking unions again, and all sorts of combinations. So now that requires a new definition of an event, which is what we will start next.